At this point, I'd like to do an unpowered curve trace of the 74HCT00 device. That's a CMOS device. It's a quad NAND gate, fairly simple to understand. To do that, I just need to bring up the unpowered curve trace form and fill in some blanks. Most of the blanks are already filled in, such as the job and the pin map that I need to use. And the curve trace method that I plan to use is going to be pins to ground. This one's more flexible because it allows me to choose which pins are grounded and which pins are curve traced independently. I like to start out with all pins curve traced and all pins grounded because this shows me at a glance if I have any opens or shorted pins, and I can go back and I can look at those more carefully and determine what shorts lead to what other pins. And the source settings, I like to curve trace from -5 volts to 5 volts. You can use a narrow or wider range if required, but this works pretty well for me. I break that up into 100 sample points, or each step is going to be 100 millivolts. And I'll do that through a 100K series resistor. This series resistor gives me pretty low short circuit current, so I don't manage to damage my device by testing it. It also gives me pretty good noise so that I can see accurately what the current is to measure leakage. The last tab I can add some special filters and delays, but I generally don't need those until I'm trying to get close to 1s or 10s of nanoamp type measurements. So with all the settings in there, I can just hit the Run Test button. Once it's done, it's going to display those curves on the screen, and I can maximize them to take a closer look. With the all pins displayed like this, I can easily see that there are no shorted pins and there are no open pins. And likewise, I can use my Trace ID tool to identify those are the output pins, and these are the input pins. And maybe here, this one here is the VDD pin. That leaves the VSS pin, must be this one right here. If I want to look at the pins individually, I can uncheck the display pins box and go and look at them one by one. And if I want to search a larger quantity of pins for opens and shorts, I have those automatic search tools here in the compare for opens and shorts. Well, maybe you've got some failure devices at this point and we're not sure exactly what curves to look for. So the best way to be to compare them to a known good device. Well, I know this device right here is good, so I'm going to save that as a control file. Give that a name. And say OK to that. And it leaves it on the screen, but now colored red so that I can distinguish those curves from other curves that will appear on the screen in just a moment. So now I've replaced the device in the socket with my failure device. It's got some leakage between some pins. And without changing any of the test conditions, I'm going to go ahead and run the test again. Now, whatever the red doesn't cover up is different from the curve that it was before. So clearly we can see that with this new device the results are quite a bit different than the original device. If we take a closer look pin by pin, we can see that pin 14 has some leakage. That's pretty obvious. And some diode shifting on some of the other pins. Some interesting curves. Just about everything has got something going on the diode shifting. But the two worst pins are going to be 3 and 14. Now 14 is a power pin. Whenever there's a failure involved with a power pin, it's not unusual to see a whole bunch of other pins changed as a result. That's because the voltage reference that those clamp diodes leads back to has been changed, and therefore the curves attached to those pins also would be changed. If I had a lot of pins, not just the simple 14 here, then I might use the automatic compare trace. In this case, anything that's more than, say, 1 microamp or 100 millivolts different, then it's going to be marked as a failure. So I hit the compare trace button, and looks like 3, 7, and 14 are the worst. Why not the other ones? Probably because my tolerance was a little bit bigger than what had been advised for these settings. At this point, I might want to save my DUT file, maybe call it serial number 1, and then go on and test another device at this point, from this point on. So maybe I'll try this failure device here, which has a little different mode of leakage associated with it. So I'm just going to run the test again. And immediately we can pretty much see that there's a pin that's pretty much shorted, and we also see a lot of differences along the other side there. Our shorted pin is going to be 7 and 14. Well, those are the power and the ground pins, so I would expect quite a lot of things to be changed as a result. In fact, just about all the other pins have some change on their ground clamp diode as a result of that. Starting out with our set of known good device curves from the unpowered curve trace of the 7400, let's try a few different test conditions and see how those change the set of curves that we have, keeping in mind that all along this device is a good device. So if we go back and we change our pins to ground so that it's just pins 7 and 14 and run the test, what we'll see is that the results that we get are very similar to the ones that we just had. And so we see our set of double diode curves. I think if we spread that out, they're going to look just like they did before. But if we look at pins here, that's 14 here, and this one right here, that's pin 7. So it's not one pin going all the way across. That's something you have to watch out for. If we look at the pins one by one, we'll see that pin 7 is just a single diode. So whenever the ground pin tries to go above the VDD pin, immediately we see a big robust diode and nothing else going on the other direction. All the other curves are double diodes, but the power pin here, so in here we're applying voltage to the VDD pin with all the other pins grounded, and at some point the current starts to increase into the microamps before we cut it off with the series resistor. You'll notice that if I do display all the pins, there's kind of a slope attaching all these pins together here. If I use this the calc slope tool and kind of measure between all those points there, we'll see that the slope of that curve over here is 100 k ohms, which you'll notice is the same as my series resistor. It means for pins that are shorted, they're only going to go up to the maximum current that the form tells us, in this case 50 microamps. And pins that are open, they can only go to about 5 volts. So every other curve is going to remain bounded by that triangle. Everything's going to stay within that area there. Another test condition we could take a look at is what happens if we just ground the ground pin, pin 7. Run the test now, and what we will see is only pin 7 is connected to the ground. And the curves that we see as a result, we see lots of clamp diodes to the ground side. Pin number 7 appears to be open because when we're curve tracing it, nothing else is connected to ground. And pin 8 seems to be shorted. It's unexpected, but that's the result that we get. And if we change that to pin 14, we'll see similar results, except now the curves on the right-hand side will be more or less regular and looking like the double diode curve, but the curves on the left-hand side are going to be all spaced out and moved around. And that's because with the VDD pin grounded, we can get through the VDD clamp diode junction pretty easily from point to point. But with VSS floating, the current that these pins source into the device have to go through some unpredictable route in order to get back to the VDD pin, and that's going to be different for each pin. So it's best always to try to make sure that you get at least your VDD and your ground pins connected when you do your curve tracing. And by using the all pins grounded connection, you're assured of doing that even without looking at your data sheet.